In this video, we're going to be covering the A-level chemistry topic of mass spectrometry. You can't talk about mass spectrometry without talking about relative atomic mass or relative molecular mass or relative formula mass. And so it's important before we start that you appreciate the difference between relative atomic mass and mass number. So mass number is for one atom. You look at a particular atom and it has a certain number of protons and neutrons, and those added together are its mass number. So mass number has to be an integer because you can't have half a proton or a third of a neutron. Relative atomic mass is probably not going to be an integer, in fact basically never, because it's an average mass of the atoms of an element in a particular sample. And so if that element has more than one isotope, then you're not going to have an integer because you're going to have some atoms that weigh a certain amount and some atoms that weigh a certain amount. And in all instances, this is compared to a scale where an atom of carbon-12 has a mass of exactly 12, and no other atom has got a truly integer mass. Provided you understand that relative atomic mass is the mass of an atom compared to an atom of carbon-12, then relative molecular mass is not a difficult concept to understand. It's exactly the same idea, just for a molecule. So if you know what atoms are in a molecule, you add up their relative atomic masses and you have the relative molecular mass. And then sometimes we want to use this same concept for something that is not a molecule. So say if you have an ionic compound like sodium chloride. So then we use exactly the same concept and exactly the same way of working it out. We just call it relative formula mass instead. But we still use the abbreviation MR, whether you're using relative molecular mass or relative formula mass. You met relative formula mass at GCSE, so this shouldn't be too difficult, but just pause the video and make sure that you're able to calculate the relative molecular mass or relative formula mass of each of these 5 substances. Hopefully that wasn't too tricky for you, and you've managed to work out that the MR of ethanol is 46 grams per mole, chlorobenzene is going to be 112.5, butanoic acid is 88, Buckminster fullerene is 720, and arsol is 127.9 grams per mole. So what even is mass spec? Well, it's an analytical technique, and what it actually does is it measures the mass to charge ratio of ions. But the ions are actually created within the mass spec. So what we're really using it for is looking at the relative abundance of either some atoms in a sample, or it could be some molecules in a sample, or there is a type where you look at fragmenting a certain compound so that you can kind of try and figure out its structural chemistry. But basically what we're looking at is how much do things weigh and how much of them is there. So there are a few different types of mass spec, and for A-level we're mainly going to concentrate on time of flight mass spectrometry. So for all of these different types, there is an ion formed, and then based on their mass to charge ratio, they're going to be separated. And there are 5 steps that you need to know about. So the sample that we're putting into the mass spec machine is going to be ionized, accelerated, drifted, detected, and then analyzed. The first step is ionization, and there are 2 methods that you need to know about. And the method that you choose is going to depend on the kind of molecule that you're working with. So electrospray ionization is sometimes called soft ionization, and basically it's a good one to use if you're looking at a large organic molecule. Because the problem is that if you use electron impact ionization, it can cause your molecule to fragment into little pieces. Now sometimes that's really useful because you want to see which pieces it fragments into, but if you're just interested in how big is my overall molecule, then you kind of want it intact. So electrospray ionization involves dissolving the sample in a volatile polar solvent. So that could be water, it could be methanol, something like that. And then what you're going to do is you're going to inject your sample through a needle, like a very, very thin hypodermic needle or something, that's connected to a very high voltage power supply. And it's important that you know it's high voltage. It's come up before as a multiple choice question. Is it high voltage? Is it high current? Definitely high voltage. So when this happens, each of your molecules gains 1 proton. And remember, a proton is a hydrogen nucleus, right? So it's a hydrogen ion. So the ion that's formed is going to have a relative formula mass that is 1 point bigger than the mass of the original molecule because it's got 1 extra proton. And it's also going to have a single positive charge because it's got 1 extra proton. And so then eventually, when that solvent evaporates, you're going to be left with just the ions and they're ready for the next stage. Your alternative method of ionization is something called electron impact, and this is more common when you're either just working with individual atoms or when you're working with very small molecules where realistically they're probably not going to fragment. So in this one, we vaporize the sample, we sort of turn it into an aerosol, into a gas, and then we fire really high energy electrons at the sample. Again, it's important that you know that they're high energy electrons. If they were slow electrons, they wouldn't do anything. And what those high energy electrons are doing is knocking outer shell electrons off of your molecule or off of your atom and forming ions that have a single positive charge. And those ions will have the same mass as the molecule or the atom that you started with, because all you've done is removed an electron, and the mass of an electron is so small it's basically negligible. It's worth pointing out that if you're using electron impact ionisation, it's technically possible for 2 electrons to be removed. And if that happens, then you end up with an M2+ ion. And you need to know that because when these ions get sorted in a minute, they're going to be sorted according to their mass to charge ratio. Now, usually their charge is +1, so their mass to charge ratio is exactly the same thing as their mass ratio. But if an ion has twice the charge, then it's almost like it's got half the mass, and it's actually going to end up going at twice the speed. So it's going to be accelerated more. So just be aware that that is an option that could happen. On AS Paper 1, it's relatively likely that you'll have anywhere from 1 to 4 marks asking you to describe part of the mass spec process. So this is a 2-mark question that just asks us to describe how ions are formed in the mass spectrometer. So pause the video and write down your answer. In this 2-mark question, we haven't specified which method you need to be talking about, so you can have the marks for either. So either you're going to say that a high voltage is applied to a sample that's in a polar solvent, or you could name an appropriate solvent, and then as a result, the sample is going to gain a proton and it's going to form an ion that is MH+. Or you can describe how the sample is bombarded by high energy electrons. Remember, those electrons have to be high energy, it's not just enough to say electrons. And as a result of this, the molecule loses an electron and therefore forms an ion that is M+. Some other questions you could be asked are to write equations for the ionisation or to think about what the mass of the ions will be. So if we're asked to write an equation including state symbols for how an atom of vanadium is ionised by electron impact, remember electron impact is about the loss of electrons, confusingly by using other electrons to knock them off. So I'm going to have my vanadium as a gas, and then it's going to be split apart to be a vanadium ion and an electron. Or we could ask about what the mass of the ion would be if we're using electrospray ionisation. Remember, that involves picking up a proton, so therefore if I've got 58 nickel, my ion will have a mass of 59. So here you've got a very simplified diagram of a mass spec, and I've got a bunch of ions which have already been ionised using electrospray ionisation. So you can see here that my polar solvent has been injected into quite a big needle, to be fair, which has been connected to a high voltage power supply, and they're going to have each gained a proton. But remember, I could also have ionised these using electron bombardment, and crucially, whatever method I'd used, I would have produced ions that have a positive charge. And I should probably point out that this doesn't depend on sort of what type of ions you think an element should make. They're always going to be positive because they've either gained a proton or they've lost an electron, and either one of those will make these positive. So because all those ions are positive, they're going to spread out because like charges are going to repel. And the next step is that they're going to move into a vacuum and they're going to be accelerated. So they're in a vacuum because we don't want those particles colliding with nitrogen molecules in the air or whatever. We want them to just move at whatever speed they should move at. So they're accelerated using an electric field, and that acceleration is going to give them all the same amount of kinetic energy, and this is really, really important. So every ion has exactly the same amount of energy. Now you hopefully remember from GCSE physics that kinetic energy is a function of mass and velocity. You don't need to remember the exact equation because when you need to use it in an A-level chemistry exam they will give you that equation, but it's kind of worth you being familiar with it and having a play with it just because it comes up fairly regularly, and whenever it does, the people who take A-level physics and are still using it all the time are completely fine, and it's a nice easy 5 marks for them. And everyone else who's not used it recently kind of is a little bit uncomfortable and just finds it much harder. So I would say it's one that's really worth being familiar with. So anyway, kinetic energy is a function of mass and velocity, and that means that if you have a constant amount of kinetic energy and the mass increases, then the velocity decreases, and vice versa. So the ions that come into this, whether that's different isotopes of a particular element or whatever it is, if there are different masses, then if they have the same amount of kinetic energy, they're going to have different velocities. The smaller, lighter, lower mass ions are going to have a higher velocity and they're therefore going to move faster, whereas the larger, heavier ions are going to have a lower velocity, so they're going to move slower. So they've been accelerated by this electrical field, and then they're going to move into a flight tube. So these positive ions are attracted to a negatively charged plate, because they're positive and it's negative, and they end up moving through a hole in this plate into this drift tube. And they're going to move through that flight tube. They're going to drift. There's nothing to collide with them, and they're going to carry on moving at whatever velocity they were moving at when they initially went into it. So the light ions, which were moving very quickly, are going to carry on moving very quickly, and the heavier ions, which are moving more slowly, are going to carry on moving slowly, and therefore they'll end up separating out. Pause the video again and jot down what the key points are in the separation of ions in the mass spec. This time around there are 4 marking points for you to get. Firstly, the positive ions are accelerated by an electric field, and they're accelerated until they have constant kinetic energy. Because they have constant kinetic energy, the lighter ions are going to have the same amount of energy, and therefore they're going to have a higher velocity, and therefore they're going to arrive at the detector first. Since I've said it's useful to be familiar with the kinetic energy equation, let's have a quick look at it. So kinetic energy is half times mass times velocity squared, where mass is measured in kilograms and velocity is measured in meters per second. So if the mass quadruples, the velocity is going to have to half. And the reason for that is that if the mass goes up by a factor of 4, velocity squared has to go down by a factor of 4, and therefore velocity goes down by the square root of 4, which is 2. Let's look at an example. This is based on an exam question, so it dots around a little bit and covers a couple of different things. A sample of chlorine was analysed and it was found to have 2 isotopes, 35 chlorine and 37 chlorine. After electron impact ionization, so remember that's the one where we're knocking off electrons, the mass isn't really going to change, all of the ions were accelerated to the same kinetic energy, as per usual, and they then travelled through a flight tube that was 2 metres long. The 35 chlorine ions took 7.5 times 10 to the minus 4 seconds to travel through the flight tube. So first part of the question, we need to calculate the mass in kilograms of 1 ion of 35 chlorine. And then once we've done that, we're going to calculate the amount of time it took for the 37 chlorine ions to travel through the same flight tube. So in the first part, we need to calculate the mass in kilograms of 1 ion. So obviously the mass of a mole of ions would be 35 grams. So I can use Avogadro's constant to work out that 1 ion should weigh that much in grams, but then I need to put it into kilograms, and remember there are 1,000 grams in a kilogram, so I end up with 5.81202 times 10 to the minus 26. In order for me to be able to use the kinetic energy equation, I need a velocity, and remember velocity is distance divided by time, so I'm just going to take my 2 metre long flight tube and divide it by the number of seconds that it took for the ions to get through that flight tube, and I have a velocity. Now this next bit is not standard nomenclature, but I just find it hard to keep track of numbers if I don't do this. So the amount of kinetic energy that my chlorine 35 isotope has will be the same as the 37, because we know that all of those ions have been accelerated until they have the same amount of energy. So I know that the equation for kinetic energy is half mv squared. So half the mass of chlorine 35 v squared is half the mass of chlorine 37 v squared. So I can get rid of the halves because they just cancel out. And then what I can do is divide my left-hand side by the mass of chlorine 37. Now I could use the individual ion mass that I've worked out in the previous part, and I could also work out the individual ion mass of chlorine 37. But actually the ratio between those two numbers is going to be 35 divided by 37, so I'm just going to stick with that. So having worked out what the velocity of my 35 chlorine ion will be, I can square that down here, and then I can use the ratio of the masses of the two ions, 35 to 37, to work out what v squared of the chlorine 37 ion will be. And then I just square root that to get a final velocity of my 37 chlorine ion. And as expected, it's sort of the same order of magnitude, but slightly slower because it's a slightly bigger ion. And then the last thing I need to be aware of is, of course, the number of significant figures that have been used in the question. So I'm going to make sure that I give my final answer to 3 significant figures as well, because that's what they've done. The positive ions drift until they reach the negative detection plate. And that plate is negative because it's full of electrons. So when the positive ions reach the plate, they each pick up an electron, and that causes a current to flow. So that current is detected, and the more ions you have of a particular type, the bigger the current will be. So the abundance of that ion is proportional to the size of the current that flows, and therefore we're able to determine what is the abundance of that particular ion. So one more opportunity to describe what's going on. Pause the video. How are the ions detected, and how is their relative abundance measured? Well, the ions are detected when they hit the negative plate because they each gain an electron. This causes a current to flow, and the abundance of the ion is relative to the size of the current. You could also just be asked to identify which ion will reach the detector first. So here's an example where we have a sample of magnesium with 3 isotopes in it, and they want to know which ion will reach the detector first. So just pause the video, scribble down what you think the right answer is. So you hopefully remembered that all 3 isotopes are going to have the same amount of kinetic energy, and therefore the lightest isotope is going to move the fastest and therefore reach the detector first. So that's magnesium 24. However, make sure that you also remember you need to be writing down 24 magnesium plus. So this happens quite often where they ask you quite a straightforward question and you've understood the science behind the mass spec, but in the heat of the moment you forget that they've asked you about an ion, so you need to make sure you actually write down the charge of the ion as well. So we're finally ready to start looking at some mass spec data. So when you do a mass spec, you get a picture out that looks a bit like this. And each one of these lines represents either a different isotope if we're looking at atoms, or it could be a different molecule or a different fragment ion. Basically, they're all ions, and they're separated out according to their mass to charge ratio. So this is what we were saying earlier about the fact that you could get something slightly funny where you get a 2+ ion, but usually it's just going to be straightforward. The mass to charge ratio is basically just going to be the mass. So here we're looking at chlorine 35 and 37, and so I have peaks at 35 and 37, and the height of those peaks represents the relative abundance. So you can get pictures like this and be asked to interpret them and work out what the relative atomic mass of a particular sample would be, or you could be given the data and asked to draw one. And then we can get some funny things. So this is a mass spec for atoms of chlorine, but of course chlorine usually goes around as a diatomic molecule. So let's say that we have a relative abundance of 3:1 for 35 to 37 chlorine atoms. So what will the relative abundance be of 35-35 chlorine molecules, 35-37 chlorine molecules, and 37-37 chlorine molecules? Well, if we actually look at the mass spec that you get for chlorine, what we see is that we've got a ratio of 9 35-35 to 6 35-37 to 1 37-37. And if you think about this in terms of sort of probability, that makes sense. If I pick out one particular atom, I have a 3 out of 4 chance that it's going to be chlorine 35. And then if I do that again as an independent event, I still have a 3 out of 4 chance. So if I multiply those probabilities together, I get 9 out of 16. In the next section, we're going to combine the mass spec data with some relative abundance data of isotopes. So before we start trying to put the two together, just pause the video and double check that you're happy calculating the relative atomic mass of each one of these samples. Hopefully that wasn't too tricky for you and you've managed to work out that the relative atomic masses are these. We've already used relative abundance data of different isotopes to work out the relative atomic mass for a particular sample, but now we're going to use this together with mass spec data to do exactly the same thing. So here I've got a sample of boron that's made up of 20% boron 10 and 80% boron 11, and I want to know what the relative atomic mass would be. Well, just like if they'd given me the data in a table rather than a mass spec readout, I'm going to work out what 20% of 10 is and 80% of 11, and then I'm just going to add them together. And that's going to tell me that the relative atomic mass of this particular sample of boron is 10.8 grams per mole. Pause the video quickly and make sure that you can do the same thing with lithium. So here I worked out what 7.6% of 6 would be and 93.4% of 7, and if I add them together I get 6.994 grams per mole. Here are two more examples for you to pause the video and have a go at for copper and bromine. Copper is 69.1% copper 63 and 30.9% copper 65, and that gives an overall relative atomic mass of 63.618. And then if we look at bromine, we've got 50.5 times 79 and 49.5 times 81, so I've got a relative atomic mass of 79.99 grams per mole. Finally, it's just worth mentioning that actually mass spec can be far more accurate than the nearest integer. So if you're using high resolution mass spectrometry, you can actually figure out what the mass of a particular molecule is down to several decimal places. And this can be really useful if you're trying to distinguish between different molecules which have essentially the same relative formula mass, but not at a very, very accurate level. So you know that nothing apart from carbon actually has an integer mass. And if you use high resolution mass spectrometry, then you can start to see the differences. So for instance, we've got 3 different compounds there, which I would essentially say have a relative formula mass of 70.1. But actually, if I use high resolution mass spectrometry, I can begin to differentiate between them. So in this video, we've looked at simple time of flight mass spectrometry, including the steps of ionization, acceleration, ion drift detection, and analysis. We've discussed using mass spec to identify the mass of isotopes and their relative abundance, and to identify elements and molecules. You should now be happy interpreting a simple mass spec of elements and also calculating the relative atomic mass from isotopic abundances. Mass spec will come up again in organic chemistry, but we'll worry about that when we get there. I hope this has been useful. Thanks for watching, and if you'd like to see more videos, don't forget to subscribe.